that we need to talk about?
1, 4, and 14.
1, 4, and 14. We need to talk about all three of those. I'm pretty sure that's because we didn't do them.
It was.
Is that fair?
Yeah.
Oh, this is the,
The ready and the go.
no, like, so no practice.
Yes, it is off at 2.9.
So like, I was saying like, oh, like,
Gotcha.
okay.
Donovan? Did you get all three of these right? Okay, I didn't hear you say that. That's my bad. So, hopefully we've seen this already. Say again?
He's out the door.
Say,
Oh, shit.
you gotta stop being tardy. Then you need to come by and say something before you go to the bathroom. You're 2 minutes late. Then come by and say something. Don't just go. But you need to use the bathroom now? You're 2 minutes late and now you're going to the bathroom? Are we serious? Where were you? Bathroom?
I was in the downstairs bathroom, but it's clogged up.
They got the thing.
They got a thing, you know, like a thing on top of it.
I have no clue what you're saying. Do you still have to use the restroom though? You better go quickly.
I'm getting my homework first.
Use them, so he has to use the upstairs.
You checking the homework?
Yeah, show it to me before you go. Okay. So,
Go to Palm Springs for the day trip.
okay, flip it over. Okay. Really quickly. I will point this out. First off, with number 1 and numbers 1 through 3, they're asking you to use what form of the equation of a line? But what is y equals mx plus b called?
Slope.
Slope
Intercept.
intercept. Right?
Okay.
I do want you to notice, and like, we've actually used this a good bit, even though you may not have realized, and I'm about to show you how in a second. But y equals mx plus b, there's two things you gotta have. You gotta have your slope, and you have to have the y-intercept. Mathematicians are not original. The name for it is that name because it is what it is. We need slope and y-intercept, so we call it slope-intercept. That's it. Now, we've somewhat written it like this, but I do want you to notice, you might have seen, or if we were to look at a graph for, you might have seen it look like this. Or if you were to look at a table, you would see it written like this. So you would probably written it sometimes like this. Hey, what am I starting at with this equation, or with this table, with this function?
0. 4.
Notice the y value is starting at 4. And then what are we repeatedly doing to that 4? What are we doing to that 4? Subtracting how much?
7.
7. How am I going to show that I'm repeatedly taking 7 away?
Multiply.
By?
M. O. G.
The independent variable. I want you to look at these two equations. Are they different? I want you to think about it. The 4 is positive. Is this 4 positive?
Yeah.
It is the same.
It is the same, right? We still have,
Swap.
it's just swapped. It's still a starting point of 4, a y-intercept of 4. I have multiplication, so what am I repeatedly doing? Multiplication is repeated
Addition.
addition. What am I repeatedly adding?
7.
Nope.
-7.
Negative 7. Are those the same equations?
Yes.
So the way you've been writing a 4 minus 7x, that's the same thing as negative 7x plus 4. We've been using slope-intercept. It's just a different way. I just need you to understand that multiplication is the repeated addition. Whatever your additive rate of change is being multiplied by your variable. And then your y-intercept is on its own. Okay? This will come up more moving forward, but what is it called when you have a slope and a point?
Point, slope, point.
Mathematicians are not original.
That's what we're talking about.
Man, I need a point, I need a slope. I'm going to call it a point slope.
Imagine.
Cool. Now, I will make this note here. If we're to look at this table, now first off, I do want you to note The point 0, -7. That's not just a point, that's also the what?
Y-intercept.
That's also the y-intercept. You could have used slope-intercept here. They were asking you to use point slope. And then I have a slope of 9, meaning I repeatedly
Multiply,
add
by 9.
9. Okay? So what I could have done is, hey, what y value am I starting at?
-7.
-7. What am I repeatedly doing to that -7? Adding 9. Hey, how am I going to show that I'm repeatedly adding 9? Well, what operation shows repeated addition? Multiplication. And because it's the 0 term, it'd be x minus 0. Is that the same exact equation?
Yes.
This point slope can be useful though because I don't have to start at the 0 term. Remember the slope-intercept, you have to start with y-intercept. Here I'm starting with what y value?
2.
Repeatedly adding 9. But it'd be x minus 1 times.
There's there you go.
These are different, they look different, but do they describe the same function?
Yes.
What term did we use yesterday to talk about things that look different but describe the same function? They're what?
Teachers, excuse this interruption. It is time for the afternoon play to start, so the students that have a blue ticket can show you their ticket and come on down to the theater.
I said
Thank
Matt
you.
cut on right.
So,
If they forget, you have
I
a
do want
list
you to
that comes
notice
across from
this
the
idea
email.
that they all look different, but they are equivalent. They're all just different point slope forms, because if it's point slope, you can use any point and the slope. Okay? So Donovan, does this make sense now? Why it's 9 times x minus 0, x minus the x value. And then it is technically plus the y value, but if you add a negative, that's the same as subtraction. We all good over there? Any questions about how I simplified number 14 to show that these were the same? Because this, and I need y'all to notice this, you need to show something that tells me you understand how to simplify this, because you could plug this in Symbolab. I need you to show me some evidence that you understand what's happening. So I need you to show me, hey, I'm distributing 2, if you're going to get full credit for this homework. It's that simple. Hey, I'm distributing 2. That's how I got 5x minus 7 plus 6x plus 2 minus 10x. Why do you think I underlined these things?
That's where you changed it.
But I'm going to go to Alan and I'm going to go to McKay. What'd you say, Alan?
I forgot how to say that. That's
Okay, McKay?
That's the spot you changed it.
You break it down some more. You just what? That's great. Like time.
Those are like terms. When I say 5 times x, what do I really mean that I'm doing? What is multiplication? What is multiplication? It's what? What did you say, Caroline? Donovan, what did you say it was? Multiplication is repeated addition, right? So how many x's am I adding right here? 5. 6 times x. I'm repeatedly adding 6 x's. So if I have 5 x's and I add 6 more x's, how many x's do I have? I've got 11 x's. Then I'm taking away 10 x's. So how many x's do I have? 1x. That's what we mean when we say 5x plus 6x. I'm repeatedly adding 5 x's. I'm repeatedly adding 6 x's. I'm repeatedly taking away 10 x's.
Then
Where do you get the -5 for
negative
what
2.
equals that?
You're gonna do that negative 7 and that 2.
Oh, okay.
So I looked at my x's, then I looked at my constants. -7 plus 2 is -5. Do we understand a little bit better how we're simplifying these expressions?
You make it understandable if you write it out. What we just did.
Huh?
If you write it, the next step.
Like if I write what stuff?
He's saying
If
like
you write the next step to that, you just jump straight
how
to
we
it.
did 5 plus 6 minus
Oh, explaining it? Yeah. So I didn't show this stuff because this is a homework that's for you to check yourself. But like for you to get full credit, you do need to explain, hey, and you can show the separate steps, but you can also just say,
11.
adding 5 and 6 x's, then subtracting 10 x's. That tells me that you understand 5x plus 6x minus 10x. That's a quick little explanation. Okay, cool, they understand that it's 1x. Then negative 7 plus 2 is negative 5. Notice, and this was important, did these expressions look like they were the same originally?
No.
But were they still the same?
Yeah.
What do we call those things that look different but they're effectively the same?
Equivalent.
Equivalent, right? What I want you to notice is they're not just equal. X minus 5 will always equal x minus 5. They're equivalent IDs. We all good?
Oh, yeah.
Cool, let's get started with today. Whoops, too far. Nope, we already submitted that, that's my bad.
That's a lot.
So, we're getting back to 2.9, making my point. We're going to look at our objectives quickly, and at the end, obviously, we'll do a quick little wrap up. You can
I
what?
can't see it well today. Normally I can see it well. My glasses.
Let's assume.
Does that make it easier?
Yes, sir.
I'll turn the lights back on when we start. I should not see mouths, I should not see noses. Y'all know how this works. We are too far into living with COVID for me to see faces and noses. Okay, Caroline, can you read our first objective?
I can show equivalency between different equations of the same line.
So can we have different equations for the same exact line?
Yes.
So if it's describing the same line, they are what to each other?
Equivalent.
Equivalent. That's what we're going to look at a lot over the next couple days. Braden, can you read our second objective for us?
I can use the point, slope, and slope-intercept forms of linear equations to create accurate algebraic representations of a line.
Okay, so we're using point, slope, we're using slope-intercept. You've done those in Algebra 1, we're getting a little bit better at it. McKay, did you read yesterday?
I can't remember.
Okay, read the third one for us today then.
I can create a graphical representation of a line given an equation in point slope or slope-intercept form.
Thank you, sir. So notice what we're focusing on is creating algebraic representations, creating graphical representations. There are other representations that you can create, like what?
Algebraic,
That's what we're doing here. Creating
Tabular.
graphical here. What other ones are there?
tabular,
Tabular,
verbal.
verbal,
Pictorial.
pictorial, right? So we want to be aware that there's all these different representations. They're telling the same story. We're just focusing on algebraic and graphical. I think everyone finished number 1 yesterday, except Caroline, obviously, you weren't here, I know. Did everyone finish number 1?
Yeah.
Okay, so let's continue working on number 2. I'll be coming around to the groups, talking with you. We'll do a quick wrap up at the end of all of these things. Don't forget number 2, right? They come up, they worked on this, they wrote the equation, and it says when they were finished, here's the conversation they had about how they got their equations. Sion said it was hard for me to tell where the graph crossed the y-axis. Why would she want to know where it crosses the y-axis? That's that y-intercept, right? Hey, Donovan, all the way up over the nose, please. So the y-intercept. So she found 2 points that she could easily read and figured out the slope, right? And so she got this equation. Zach used 2 other points and he got this equation. Looks a little bit different, right? One of us must be wrong because yours says that you add 9 to the end and mine says that you subtract 9. How can we both be right? Your job is to say, what do you say? Can they both be right? Show some mathematical work to support your thinking. Here's a bigger view of that graph because I know it's a little small on your paper. Alright, so start working with your group. Actually take 60 seconds, think on it on your own, and then start talking about it with your group. Linnea, since we're missing Mona, do you